Welcome you all. This is Jitendra Kumar and we will start the reverse coordinate reference system. So before starting the reverse coordinate reference system, first of all we need to understand some basic fundamentals so that it could be understood easily. So first of all we need to understand what is refrigeration. So for understanding the refrigeration, we can see one beautiful example in our house. In domestic refrigerator, you can see that what is the main purpose of this domestic refrigerator. The purpose of refrigerator is to maintain the lower temperature inside the refrigerator with respect to surrounding, with respect to outside, right? So this is called refrigeration. So what is refrigeration? Refrigeration is the process of producing lower temperature with respect to surrounding. Refrigeration is the process of producing lower temperature with respect to surrounding. In domestic refrigerator, our purpose is to maintain lower temperature inside the refrigerator with respect to surrounding. This is called refrigeration. So this is the process of producing lower temperature with respect to surrounding. Next term is refrigerant. So what is refrigerant? Refrigerant is a substance. There are different types of refrigerant, like just we'll study in further lectures. R11, R12, R134, ammonia. There are different types of refrigerant. So what is this refrigerant? Refrigerant is a substance which is used to extract heat from the storage space so that lower temperature could be maintained inside the system. So in domestic refrigerator, we have to maintain the lower temperature inside the refrigerator. For this purpose, this refrigerant will be used so that it extracts heat from the storage space in order to maintain lower temperature inside the refrigerator. So this is called refrigerant. So it is a substance which extracts heat from the storage space and produces lower temperature, right? Next term is refrigeration effect. For understanding the refrigeration effect, just we have discussed earlier, this refrigerant is a substance which extracts heat from the storage space and produces lower temperature. So this is whatever amount of heat is extracted from the storage space, this is called refrigeration effect. Whatever the heat which is extracted from the storage space so that the lower temperature could be maintained inside the refrigerator, this is called refrigeration effect, right? So it is the amount of heat which is to be extracted from the storage in order to maintain lower temperature, right? So this is the diagram of this one. This diagram, it can refrigerator, right? This is the, in this refrigerator, this work input is required to run this refrigerator. If this work input is done in this condition, this Q2 amount of heat is extracted from the lower temperature. Because this is the refrigerator, this work input, it is required to be done. This Q2 amount of heat is extracted from the lower temperature and this Q1 amount of heat is rejected to higher temperature. So this is the refrigeration effect, means this amount of heat, this is Q2 amount of heat, it is required to extract from the storage space. This is our storage space. This Q2 amount of heat is required to extract from storage space so that this temperature, lower temperature, could be maintained. So in this diagram, this refrigeration effect will be Q2. And in this condition, our system will be this one. This sink will be our system. Why? Because we have to maintain the lower temperature to the sink. So in this diagram, what is our refrigeration effect? Our refrigeration effect will be Q2. Okay, so this is very important. In this diagram, our refrigeration effect will be Q2, because this amount of heat is extracted from the storage space so that this lower temperature could be maintained. So this is called refrigeration effect, right? So one of the basic, very basic term of whenever we study any types of refrigeration system, the coefficient of performance we need to define. This coefficient of performance, this COP. COP is the ratio of refrigeration effect to the work input. It is the ratio of refrigeration effect to the work input. So what is in this condition? This refrigeration effect is Q2, because this Q2 amount of heat is required to extract so that this temperature, lower temperature, could be maintained. So this is what is our Q2. This Q2 is RE, and this is the ratio work input. This is work input. So this refrigeration effect, this is the ratio of refrigeration. COP is the ratio of work input. In addition, we can say that it can be seen that what is work input? Just you can apply common sense, because whenever any refrigerator is running, we need to supply some power input. Whenever you might have seen the refrigerator in your house, this one electrical cable is there. When you supply this electrical power, as you supply this electrical power, the refrigerator starts running. Okay, so this is called work input. This is power input. Okay, so this relationship between COP and running cost. What is this running cost? Running cost stands for this power input. Because if refrigerator runs 10 hours, that means you have to supply this electrical power for 10 hours. If you supply the refrigerator for 10 hours, that means it will consume more electricity. It will consume electricity for 10 hours. If you suppose that if any person runs refrigerator only for 2 hours, that means he is supplying electrical powers only for 2 hours. In that condition, this running cost will be less. So the COP, from this equation, it can be seen that the COP is inversely proportional to work input or power input or electrical power supply, okay, or running cost, because power input is directly proportional to running cost. If you supply power for more duration, this running cost will be more. So therefore the COP is inversely proportional to running cost, right? For having higher COP, running cost should be less. If you suppose that if this refrigerator, suppose that COP is more, that means running cost will be less, right? So this is the relationship between this COP and, so this explanation has been given here. COP is RE by work input. If work input is less, COP will be more. That is work input directly linked with power input, and power input linked with running cost. So if for lower work input, this running cost will be less and COP will be more. Next beautiful term is unit of refrigeration, because we have explained this refrigeration, we had explained refrigerant, we had explained refrigeration effect. Next term is what is the unit of refrigeration. Unit of refrigeration is TR, ton of refrigeration. What is this TR? This is one of the beautiful example. Whenever you go to purchase AC, okay, then the seller asks how much TR of AC you require. That means whenever you go to purchase any types of window AC or a split AC, you will have so many of choices, either to opt 1 TR, 2 TR, 3 TR. There are different ton of refrigeration of AC are available in shop. So you have to decide how much TR of AC is required. So this is TR is the unit of refrigeration, right? So for understanding this TR, first of all, just we are explaining one beautiful examples so that it could be understand in better way. Suppose that we are taking 1 ton of water which is at 0 degree centigrade. We are taking 1 ton of, because it is used ton of refrigeration. Okay, so remember, this is ton of refrigeration. That means, what is the meaning of ton of refrigeration? Initially you are taking 1 ton of water which is have temperature at 0 degree centigrade, and you have to convert this water into ice at the same temperature. What you have to do? You have to convert 1 ton of water which is at 0 degree centigrade into 1 ton of ice without changing the temperature. That means, what you have to do? You have to withdraw heat from this water. What is your target? You have to convert 1 ton of water which is at 0 degree centigrade to 1 ton of ice which is at 0 degree centigrade in 24 hours. There is a time restriction. We have to convert this 1 ton of water to 1 ton of ice without changing the temperature in 24 hours. In this condition, what you have to do? You have to extract heat from the water so that it could be converted into 1 ton of ice at 0 degree centigrade in 24 hours. For this desire, we have to suck 3.5 kilojoule of heat per second from 1 ton of water which is at 0 degree centigrade. If you suck 3.5 kilojoule of heat per second from 1 ton of water which is at 0 degree centigrade, it will convert into 1 ton of ice at 0 degree centigrade in 24 hours. So this is called TR, 1 TR. So what is 1 TR? This 1 TR is equal to 3.5 kilowatt or 3.5 kilojoule per second. It will convert in kilojoule per minute. This is to 10 kilojoule per minute. So what is ton of refrigeration? It is the amount of heat which is required to extract 1 ton of water initially at 0 degree centigrade in order to convert 1 ton of ice in 24 hours at 0 degree centigrade. This is called ton of refrigeration. So this is unit of refrigeration is ton of refrigeration. Whenever plant this capacity plant is given in TR, it represents refrigeration effect. Of course, we have already we have seen this refrigeration effect. This is RE. So the plant, suppose that capacity plant is 2 TR. That means 2 into 3.5. That means, what is this refrigeration effect? 7 kilowatt. Suppose that so whenever capacity plant is given in TR, it represents refrigeration effect, right? Now we are ready to move to understand reverse Carnot Ref. Okay, so we have gone through some basic fundamental like refrigeration, refrigerant, refrigeration effect, and unit of refrigeration effect. Right now, we'll discuss reverse Carnot refrigeration cycle. Basically, it consists of 4 components. This is compressor. This compressor installed between 1 and 2. Next component is condenser installed between 2 and 3. Next component is expander installed between 3 and 4. And last component is evaporator installed between 4 and 1. Okay. So first of all, this refrigerant enters into compressor at point 1, and this compressor isentropic compression takes place. This process 1 to 2 is isentropic compression. Isentropic compression takes place in compressor in process 1 to 2. This compressed refrigerant now enters into condenser where, remember, where constant temperature heat rejection takes place. This heat is rejected at constant temperature. This temperature is TH. This condenser temperature is TH. This heat is rejected from condenser at higher temperature. Okay. After rejecting heat this from the condenser, this refrigerant now enters into expander where it expands isentropically. So process 3 to 4 is isentropic expansion. Remember, this process 3 to 4 is isentropic expansion. This refrigerant expanded isentropically, and at the end of this expansion process, this refrigerant now enters at point 4 in evaporator. In evaporator, constant temperature heat absorption taken place. This 4 to 1 is constant temperature heat absorption process. So process 1 to 2 is isentropic compression. Process 2 to 3, the constant temperature heat rejection. Process 3 to 4 isentropic expansion, and process 4 to 1 is constant temperature heat absorption. Right? So this is the reverse Carnot refrigeration cycle on TS plot. So basically it consists of 4 components: compressor, condenser, expander, and evaporator. Right? This compression, in compressor isentropic compression takes place. In condenser, constant temperature heat rejection takes place. In expander, isentropic expansion takes place, and in evaporator, constant temperature heat absorption takes place. This heat is absorbed, heat is extracted from storage space. Okay, heat is extracted from storage space. This heat is absorbed at TL, heat rejected at TH. Right? So this is the, now we'll define the COP. We know that COP, what is this COP? COP we have explained earlier. COP is the ratio of refrigeration effect to work input. So what is the refrigeration effect? Refrigeration effect is QA, because Q amount of heat is required to suck from storage space so that this temperature could be maintained. So in this condition, this refrigeration effect is QA by work input. And what is this QA? In energy balance equation, QA plus work input is equal to QR. Okay, what is this? QA plus work input is equal to QR. So therefore this work input is equal to QR minus QA. So therefore this work input is equal to Q rejected minus Q absorbed. Okay, and this is the basic COP of all refrigerator. Okay, COP of all refrigerator, because this Carnot process is Carnot Ref System. All 4 processes are reversible. Okay, because this is a reverse Carnot cycle. We know that in Carnot cycle, all whatever processes are there, all processes are reversible. So we need to remember this one. So in this condition, what we are observed here, this COP is equal to heat absorbed divided heat rejected minus heat absorbed. This is COP of all refrigeration system. Okay, but we are discussing reverse Carnot Ref system and reverse Carnot refrigeration system. We know that all 4 processes are reversible process. Therefore for in this condition, as per Clausius inequality, just Clausius inequality we have studied about this one, the cyclic integral of del Q by T is less than equal to 0. So there are 2 conditions, less than and equal to 0. Since all 4 processes are reversible, this is the reversible cyclic process. In this condition, cyclic integral del Q by T is equal to 0. So in this condition, this QA amount of heat is added at lower temperature. This Q amount of heat is added. That's why this positive sign is taken. And this QR amount of heat is rejected. QR amount of heat is rejected at higher temperature. Therefore, this heat is rejected. So as per sign convention, you can write here. This is minus QR by TH. This is equal to K. Okay, this is equal to, okay, this is equal to 0. If you subtract, this will 0. If it, because after simplification, this Q by TL is equal to QR by TH. This is equal to K. So in this condition, QA is equal to KTL and QR is equal to KTH. After putting this value, you will get COP is equal to TL by TH minus TL. So this is the basic formula of COP of reverse Carnot refrigeration system. This lower temperature divided that higher temperature minus lower temperature, right? So this formula is only for reverse, remember, reversed Carnot refrigeration cycle, right? Reversed, okay. For general equation, we have COP is equal to QA by, this is RE by work input, or heat absorbed divided by heat rejected minus heat absorbed. Since this is a reverse Carnot cycle, in this condition, this equation can be written in terms of temperature. COP of this reverse Carnot cycle will be maximum because it runs on reverse Carnot cycle, because all 4 processes are reversible and this runs on reverse Carnot cycle, therefore COP will be maximum, right? And the next important point is we have to discuss how to improve this COP of reverse Carnot cycle. We have to improve, suppose that you want to improve the COP of this reverse Carnot refrigeration cycle, then how will you improve? You have this basic formula, COP is equal to TL divided TH minus TL. Suppose that if you fix the TL in this equation, if you fix the TL, then how will improve the COP? If TL is fixed and if decrease the TH, then what will get? This denominator will be less. If TH is less, denominator will be less, and because this TL is fixed, in this condition the COP will improve. For lower higher temperature, if you fix the lower temperature and if higher temperature is decreased, in that condition COP will maximum. This can be seen in winter condition. What is higher lower temperature? Lower temperature is the temperature inside the refrigerator. What is the higher temperature? Higher temperature is temperature of this outside temperature. Okay, so if lower temperature is fixed, that means if the temperature of inside the refrigerator is fixed, suppose that if you want to maintain the temperature of this refrigerator at 10 degrees centigrade, that means this is fixed. And in winter, what you observe, outside temperature is low with respect to summer, because in summer this temperature might be up to 45 degrees centigrade. In winter, the temperature, suppose that is 20 degrees centigrade. In this condition, if with respect to summer, if this higher temperature is low, so if higher temperature is low in winter, in this condition what will happen? COP will be more. Therefore, it can be said that in winter condition, in winter COP will be maximum. COP will be more with respect to summer, because in summer this THI will be higher. Okay, so therefore this is our important observation. So if TL is fixed, if you decrease the value of TH, the COP will be more. If, for example, this condition might be seen in winter condition. If TH will increase, like in summer condition, if for fixed TL, the COP will decrease. Next condition, if suppose that if TH is fixed, if higher temperature is fixed, in this condition, if you decrease the TL, this COP will be more. Okay, if TH is fixed, if you increase the, if you increase the TL, in that condition COP will be more. Right. For fixed TH, if lower temperature is increased, that means if you inside the temperature inside the refrigerator is increased, suppose that if you have to maintain if higher temperature fixed, that means outside temperature, let us suppose the outside temperature fixed at 30 degrees centigrade, and there are two conditions. In one condition, you have to maintain the temperature of fridge for 10 degrees centigrade. In another condition, temperature you have to maintain the fridge at 15 degrees centigrade. In that condition, if temperature lower temperature is more, the COP will be more, right? Therefore, it can be said that COP in winter is greater than COP in summer. Okay, this is we have already discussed. Of course, if in winter the COP will be more, of course this running cost will be less, because COP is inversely proportional to running cost. So for higher COP, running cost will be less. Therefore, it can be said that in winter, since COP is more, therefore running cost will be less with respect to summer, right? Okay, this is all about our this first session. We will meet in next session. Thank you.